So fully understanding the proof of the singularity analysis is certainly deep water and complex analysis. But as promised, now what we're going to do is look at some general schemas that in applications will free us from a lot of that difficulty. So it seems like a lot of work approximating a function and checking delta analyticity and other things. The question is, are there any shortcuts? And the answer is yes, that the process is really automatic for a broad variety of classes. And we'll look at some examples. We saw one of these in the previous lecture, where we refer to a treatment that unifies the analysis of a family of classes as a schema. And now we're going to look at examples of schemas that are amenable to singularity analysis. They get us into the top level of analytic combinatorics, where we can go from the spec to the equation via the schema right to the coefficient asymptotics. So last lecture we looked at the supercritical sequence schema that handled via meromorphicity all constructions of the form f equals sequence of G. Now we're going to look at the, for singularity analysis, we're going to look at analog for label classes called the xblog schema that handles f equals set of G. We'll look at what's called simple variety of trees, and again there's a technical condition called invertible, and that will handle things like unary binary trees and many other things. And we'll look at so-called context-free schema, which handle families of constructions that are quite common for unlabeled combinatorial classes, and they're the technical conditions called irreducible. So if we have a problem that falls within one of these schema, then we have an easy way to solve it. So let's look at labeled sets. So again, this is similar to supercritical sequence, except it's for sets. So if you have a labeled class that has a construction of the form f equals set G, where G is another labeled class, so that's a labeled set class, or it falls in the labeled set schema. The generating function, just by symbolic transfer theorem, we get f of z equals e to the g of z. So if f of n is the coefficient of z to the n f of z, it's labeled so the number of structures is n factorial f of n. We can also work with parameters by marking things with another variable u, making it bivariate. So if you want to mark the number of g components with u, then you can do either the ug of z or the number of g components of size k, and there's lots of things that we can do with parameters as well. But just focusing on enumeration, f of z equals e to the g of z. And so now there's some technical conditions that we can check that the construction or the generating function coming from the construction satisfies. And if it satisfies these technical conditions, then we can get a quick analysis. So we say that it's xblog with parameters alpha, beta, and rho if the generating function for G, for the ones that we're taking sets of, satisfies these conditions. So it's going to be analytic zero, non-negative coefficients. So that's pretty much automatically satisfied for combinatorial generating functions because we're counting things that coefficients are non-negative. Finite radius of convergence rho, so that has to do with whether it has a singularity or not. And then if there's similar with what we saw for meromorphic and other applications, if there's a lot of singularities the same distance from the origin, then you have complicated periodicities. But in a great many applications, it's got a unique singularity on its radius of convergence. And then there has to be a delta domain for the G function at rho. That has to be checked. So these are all technical conditions that are required in order for the singularity analysis proof to go through. And for many applications, these are very easy to establish. And then the other condition, which is not a general condition, but it's one that holds in lots of applications, and that's what xlog, this is the log part of xlog. And basically it says that you can approximate G with a log with various parameters. So alpha times log of 1/1 minus z over rho plus beta, those are the parameters. So, and sometimes it's actually equal to a log function, in which case you can put, and actually many of the applications will do, it's equal, in which case you can pull the parameters right out. So that's the log part. The x part comes from it being a labeled set. So those are the conditions, the technical conditions that if it's satisfied, then we say that the thing is xlog. So for example, the generating function for cycles is log of 1/1 minus z. So, and that's analytic, and that's its domain, so the first few conditions work. And it's equal to log of 1/1 minus z, so that means alpha equals 1, rho equals 1, and beta equals 0. So the set of permutations, which is sets of cycles, is xlog of 1/1. And that's an easy one, and then we have more complicated ones. But still plenty of classes where if you can have a set of things that you can approximate with log, then we have a transfer theorem. And here's the transfer theorem for xlog labeled sets. So it's some kind of set, it's xlog with parameters alpha, beta, and rho. So that means that G is approximated with alpha log 1/1 minus z over rho plus beta. If that's true, then just doing the transfer through the exponential f of z is approximated by e to the beta 1/1 minus z over rho to the alpha, which again applying standard function scale transfer gives the coefficient of z to the n and f of z. So you just have to figure out those parameters alpha, beta, and rho that the generating function for G is approximated for, and you have the coefficient asymptotics. Not only that, for such classes, the proof shows that the number of G components is going to be alpha log n. That's true for any xlog class. In extremely brief proof sketch, really not at all, it's really those conditions match up with the basic singularity analysis process, and it's just applying the singularity analysis in this general setting. And you can see that the conditions of delta analyticity and so forth match up, so I'm not going to go through that detail. So most people for applications are just going to remember that one formula. Going to need to remember just that one formula for xlog labeled set classes. So for example, trivial example, but still to check the method, this is using that schema to develop asymptotics for the class of all permutations. So permutations is a set of cycles. So that's the xlog form. Now G of z is log of 1/1 minus z. So we're going to apply the theorem and find that alpha equals 1, beta equals 0, and rho equals 1, as I said. So we get the asymptotics immediately. E to the beta is 1, gamma of 1 is 1, 1/rho is 1. All that we have left is 1. So that says that the average number of permutations is n factorial. But more important, if we apply the corollary, then we immediately get that the average number of cycles is approximated by log n. So that's using the schema to find the average number of cycles in a permutation. And that's, again, we have lots of other ways to get that easy answer. We'll look at many, many more examples in the next lecture of applying the Xblog label set schema. Here's another example of a schema, simple varieties of trees. So we say that a combinatorial class, if it's a numeration generating function, satisfies f of z equals z times phi of f of z, then it's a simple variety of trees with characteristic function phi. And again, we're going to have technical conditions on such functions that will enable us to get a general theorem to get coefficient asymptotics for such classes. And this one works either if they're unlabeled or labeled. So for unlabeled, then it's coefficient z, the n of f of z is the number of structures. And then we have constructions like z times sequence omega. So sequence omega just means omega is a set, and you pick the ones out of that set that you want, sequence of length k, k1, k2, where they're in that set omega. And we've seen that in plenty of examples. In labeled case, then it's n factorial times coefficient z, the number of structures. And instead of Cartesian product, we use the star product. But all of those things lead to a generating function equation of this form immediately by symbolic transfer, where this function phi depends on which integers are in the set omega. And we'll look at examples of that, and we have seen examples of that before. Now again, we need a technical condition in order to be able to prove a transfer theorem, and for tree classes it's called invertible. Again, we have a parameter, so we're going to say it's lambda invertible if the characteristic function satisfies these conditions. Again, it's going to have non-negative coefficients, and it's got to be non-trivial. So phi 0 plus phi 1u would be trivial. It's got to be analytic, and it's got to have radius convergence, and phi of 0 is going to be not 0. Those are just removing degeneracies. So here's the key technical condition. That we have what's called the characteristic equation. Phi of lambda equals lambda phi prime of lambda. The characteristic equation is phi of u equals lambda phi prime of u, and that's got a solution lambda, positive real root less than r. So for example, let's look at just rooted ordered trees. Again, an elementary construct that we've seen many times. So that's g equals z times sequence of g. Generating function is z over 1 minus g of z. So phi of u is 1 over 1 minus u. Phi prime of u is 1 over 1 minus u squared. So the characteristic equation is this equal to lambda u times that. So 1 over 1 minus u equals u over 1 minus u squared. And that's true for u equals 1/2. So the root of that equation is lambda equals 1/2. So therefore, rooted order trees are 1/2 invertible. So that's a technical condition. That characteristic equation has to have a real root, and it has to be non-degenerate, is really what the other ones are saying. So now we have a transfer theorem. If you have a simple variety of trees and it's lambda invertible, then boom, we have the coefficient asymptotics as a function of lambda. The exponential growth rate is phi prime of lambda, and the constant is 1 over square root of 2 pi phi double prime of lambda over phi prime of lambda. And that's all we have to know for simple varieties of trees, and that covers many, many combinatorial classes. Now the proof is deep water. It uses so-called analytic inversion to develop an approximation to the function, and then use singularity analysis, a standard function scale, to get the translation done. And it's just important to note that kind of amazing, the end of the 3/2 factor shows up for all kinds of trees. So for example, and actually the gamma function, square root of pi, shows up too. One point I haven't been mentioning is that there's a condition of periodicity that's discussed in the text that I'm ignoring here in the lecture. Okay, so let's show analytic combinatorics for trees using the simple variety of tree asymptotics. So that's the construction, that's the generating function. Then we just look at the theorem and we figure out what lambda is. Lambda is 1/2, and then we plug into the equations that we developed for phi of u, phi prime, and phi double prime. And so like lambda prime is 4, so it's going to be 4 to the n. And then the ratio of phi prime, phi double prime over phi prime is 8. So, I'm sorry, phi double prime over phi is going to be 8, so we have 16. So boom, we can get the coefficient asymptotics. The n to the minus 3/2, the 4 to the n, and then the 1/4 square root of pi comes out immediately. And our running example from before, unary binary trees, now we have different things that we allow in the size of objects in the sequence. So we're going to take either 0, 1, or a number of objects in the sequence. We're going to take either 0, 1, or 2. So that's our generating function equation. So now we immediately apply the theorem. We don't have to solve. We just immediately apply the theorem. So our characteristic function is 1 plus u squared, z phi of z. First derivative is 1 plus 2u. Second derivative is 2. The characteristic equation is 1 plus lambda squared equals lambda plus 2 lambda. Solve that for lambda, and actually lambda equals 1 solves that. So then phi of lambda equals 3, phi prime of lambda equals 3, phi double prime equals 2, the constant 2. So that means the exponential growth factor is 3 to the n. We have the n to the minus 3/2 ratio of phi double prime to phi and 4/3, and boom, we have the coefficient asymptotics. 3 to the n, n to the minus 3/2, and we have the coefficient. So this theorem can enumerate any kind of tree. And that's, next lecture we'll look at lots more examples, but it's very significant. When we looked at unary binary trees using singularity analysis, we had a fair amount of work to do. We needed to solve that polynomial equation. If it goes out to 4th and 5th degree, it might be hard to solve. We needed to expand the function around the singularity. That might involve some calculation, might need a computer. We need to check analyticity and so forth. We still kind of have to do that, but many people skip that step at least the first time through. But when we use the schema and the general theorem, it's completely plug and chug. You figure out phi, you figure out its derivatives, solve that characteristic equation, plug it in, and you have the coefficient asymptotics for any variety of tree. And the schema does its job. It unifies the analysis for an entire family of classes. And using this theorem, you don't have to know much about complex analysis to apply it. You just use the characteristic function, solve it, gives you the exponential growth, and then you compute the constant from derivatives of the characteristic function, and you're done. And again, it's a very surprising fact that you're going to have this into the minus 3/2 factor, and also the square root of pi factor, which goes all the way back to gamma of 1/2 for all kinds of trees. And there's many other schemas that have been developed. I'll just talk about one more right now, so-called context-free classes. So if you have a family of constructions where each line involves only Cartesian product and plus for unlabeled classes, that corresponds to context-free grammar from computer science, and we call it a context-free class. And we can develop a general transfer theorem for context-free classes. So for example, and computer scientists will be familiar with these kinds of examples. There's many of them out there. Say we want strings with equal numbers of zeros and ones. Here's a family of constructions for strings with equal number of zeros and ones. And so to understand this, if you want, U is a set of strings where the number of zeros is bigger than the number of ones in any prefix, and D is a set where the number of ones is bigger than the number of zeros in any prefix. And then, so you take a U, the number of zeros is bigger, but then it runs out, so you need a 1, and then you take a D, and the number of zeros is bigger, so you take a 0, and so forth. So these constructions kind of illustrate this idea. And anyway, that's about context-free grammars. And there's many examples that people have studied. But in the present context, there's the idea that there's, again, a technical condition that allow us to unify the analysis of context-free classes. And this one is maybe not familiar to people who are not familiar with computer science or graph theory. All it says is that the dependency graph is strongly connected. Well, it's nonlinear. They have to be things multiplied together, and its dependency graph is strongly connected. Strongly connected, so that just means dependency graph is for every production in the grammar, we draw an arrow to anything that's used on the right-hand side. So S uses S and D and U. U just uses U and D just uses D. Strongly connected means there's a directed path from any node to any other node. In this case, there's no directed path from U or D back to S, so that's not strongly connected. Not irreducible, that example. Here's another example, so-called non-crossing forest, and that one is strongly connected. So that's the condition, and that's a natural condition, it turns out. And then given that condition, if we have an irreducible context-free class, then first part of the theorem is that the generating function has a square root of singularity. And then there's another aperiodic condition, but then we have a unique dominant singularity, and again we get square root of pi, whenever we wrote at the end to the minus 3 halves, asymptotics, where alpha is a computable real. And so amazingly, general transfer theorem, any context-free class is going to have this same asymptotics as trees did. And at a very high level, it's maybe understandable that it would be that way because a derivation in a context-free grammar is kind of tree-like. But still, this is a very deep theorem. The basis for it is something called the Dermota-Lally-Woods theorem, and that's very, very deep water that I'm not even going to try to characterize in this introductory treatment of analytic combinatorics. And computing the constant even for such classes can be complicated and maybe is best left for a computer. So I'm not even going to give applications of this in this introductory treatment because there's a lot of things that have to be checked for this. That's not introductory analytic combinatorics. But still, it's important to know that the existence of such a theorem is this square root of pi n to the minus 3 halves asymptotics is really universal in a very broad sense, and it's proven for many, many examples of combinatorial classes. So in summary, singularity analysis is a fine example of if you can specify it, you can analyze it. It's a very effective approach for developing transfer from GF equations to coefficient asymptotics. Now the analysis can be detailed and burdensome, but we have schema that can unify the analysis for entire families of classes. And we saw 3 examples, the labeled set schema, the simple variety of trees schema and the context-free schema. They all have technical conditions involved, but they cover a very broad family of constructions, and they all wind up with the same sort of coefficient asymptotics. And in the first two cases, the computation of the constants are easy. In the second one, it can be in particular examples. If you can specify it, you can analyze it. And singularity analysis is a very deep and important method that supports this statement of Philippe's. There are plenty of other schemas, and I don't have time to talk about them all in this introductory treatment. We'll talk about another one in the next lecture. So that's an introduction to schemas and transfer theorems based on singularity analysis.